Now we're going to talk about more nonlinear functions and their graphs. So objectives, it says learn terminology about polynomial functions, find extrema, identify symmetry, and determine if it's odd, even, or neither. So constant, linear, and quadratic functions are examples of polynomial functions. Here's the general definition. So don't get all overwhelmed. So this right here is the general definition of a line, a quadratic function. This constant is technically a horizontal line. And let me just keep on reading here. It says where each coefficient is a real number, a sub n, and a sub n can't be 0. So where is the a sub n that they're talking about? So a sub n is a leading coefficient. It's the number in front of the variable with the highest power, and it can't be 0. And n is a non-negative integer. So the n that they're talking about, hang tight, this n is the highest power of the variable. So let me highlight. So the leading coefficient is a of n again, and the degree is n. The domain for a polynomial function is all real numbers. The graph is continuous and smooth without breaks or sharp edges for any polynomial function. So if I were to take out my graph here, so let me show you. If I were to do y is equal to -3, yep, it's smooth, no sharp turns or edges. If I were to do -2/3 x plus 5, hang tight, that's not what I wanted. -2/3 x plus 5. Again, smooth, no breaks. If I were to do 3x² plus 5x minus 6, yep, it's a parabola. Smooth, no breaks, no sharp turns. And what if I were to do -x to the power of 3 minus 5x plus 4? And if I were to zoom out here, again, smooth, it is continuous, no breaks, sharp edges. And one last one, what if I were to do x to the power of I don't know, 6? Yep, it is continuous, no sharp turns or edges. And if I were to add other terms, could do 5x², still looks minus an x plus 7. So they are all, let me go back to the notes here. Again, continuous, smooth without breaks or sharp edges. Functions that contain radicals. So radicals, you're used to, I'm going to circle them here. It's sort of like the square root of x. And it'd be nice for us to remember that really there's an understood 2 right here, and there's an understood 1. And I can rewrite any radical as a fractional exponent. So I'll have the 1 in the numerator, and then I'll have the 2 in the denominator of the exponent. Just a little reminder. We can also have ratios, sorry. So for example, if I have 1 over x, or absolute values, so this one is absolute value of x. These are considered nonlinear functions, but they are not polynomial functions. All right, absolute and local extrema. Sorry about this space here. So it says, let C be in the domain of f. So it's some x value. We're going to call it C. And it says the absolute global maximum is going to be the highest possible numerical y value of the entire graph. So for absolute or global maximum, it's the highest possible numerical y value of the entire graph. And a minimum, the absolute minimum or global minimum, they're synonyms, it's going to be the lowest possible numerical y value of the entire graph. Now, contrast this to what we call local or relative maximums. They're the highest point, still the numerical y value, but of an interval. And what is an interval? It's just a part of the graph represented by hills. And I put here, it cannot be an endpoint. Local or relative minimums are the lowest possible numerical y value of an interval, again represented by valleys. Not again, it's the first time I say it. Sorry about that. And note, it cannot be endpoints as well. So let's practice this right here. So it says examples. Use the graph of f to estimate the local and absolute extrema. Okay, so for the absolute extrema, we have a max. Actually, I'm going to do it in colors here. This is going to be our max right here. So our max is actually 2. So where did I get this 2? So this point is negative 2, 2. And again, the maxes and the mins are going to be the y values. So we have an absolute max of 2 at x equal to negative 2. Moving right along, we're going to have, an absolute min. So I'm going to pick another color here, taking this really slow. We're going to have a min, right here. And this value is 1, negative 2. So the absolute max is the absolute highest point, and it's the y value of that point. The absolute min is the lowest point on that graph, and the answer is the y value of it. So again, so the min is going to be negative 2 at x equal to 1. And so let me highlight here. It's going to be -2 because it's the y value at that lowest point. We're going to do 1, and it's that one right there. Now, local extrema. Hang tight. So our local extrema are categorized by hills and valleys. So here on this one, for our local, our max is still gonna be, oh, I'm gonna put another point here, right here. We could, if I'm just looking at the left part of the graph, I'm gonna have a local extrema right here. So it's gonna be a max of 2 at x equal to -2. And I'm still gonna highlight it with the same colors. That's not the same color. Why it changes it, I don't know. But we also have another local max, aka another hill. So I am going to write that one in purple. So here on this one, I have another local max, and I have it right here. And this is gonna be 2, 1. So I'm gonna have a local max of 1 at x equal to 2. So let me highlight those. So this y value right here is this one. And at x equal to 2, is that one right there. Excuse me. And then I have a local min at the, let me pick my color palette here. I'll do this one. I have a local min of -2 at x equal to 1. And it happens to be this point right here as well. So let me get the color coding here. So here's the 1, and this one is -2. So you could pause the video and try to do this next one on your own. If not, yeah, I'm gonna move on forward here. All right. Hang tight. So before I move on to the next problem, I just need to reiterate right here. I'm gonna highlight it. Local max and mins cannot be endpoints. So just make sure we know that. So the next problem. So we're gonna do the absolute extrema. Oops. So our max is going to be the highest point. So our max is going to be right here. And this point is -2, about maybe 2.6. So that means we have a max of 2.6 at x equal to -2. So let me highlight here. 2.6 is this 2.6, and at x equal to 2, -2, excuse me. There we go. And then our min Well, if you notice, these arrows go forever down. So, um, our min is negative infinity, and some people interpret that as saying, well, you can't put a number on negative infinity, so they also say it does not exist. There is no absolute minimum. All right, so the next one is the absolute, not absolute, excuse me, local. So the local extrema are the hills for the max and the valleys for the mins. So I'm gonna have a local max technically at the same point that's in green. So I'm going to go back and put it green. Then I'll use the other one as blue. So I'm gonna have a, sorry. I'm gonna have a max of 2.6 at x equal to negative 2 if I was only looking to the left part of that graph. And so let me highlight here. But I also have, if I were looking at the right part of the graph, I have a little hill right there. So this is gonna be 1 comma perhaps 0.5. So I'm gonna have another local max of 0.5 at x equal to 1. So let me highlight there. Oh, it's almost the same color, sorry. Now my local min, I do have a local min, and my local min is this point right there. It's a valley. It's a valley. So my local min, let me put it here, is 0 at x equal to 0. Because the coordinates for that point is that. And so just to make sure that we are picking the right ones, let me highlight here. So it's the y value. So there it is. And my x value is the one that is left. And so that one I'm just going to put it like that. All right. Moving right along. So now we're going to talk about symmetry. So you can have really two types of symmetry. Either it's going to be even, or it's going to be odd. And if it's either one, if it's not either one of those, then we just say neither or neither. All right, so for even functions, part A says, graphically, graphs are symmetric with respect to the y-axis. So we just finished doing transformations in the previous lesson, so hopefully we know that if we reflect it across the y-axis, it's like we're flipping it, if I were to be able to show you with our hand, from left to right, just flipping it over. Algebraically, it says here that f of negative x is equal to f of x. And I put here, note, you must use this to check non-polynomial functions. Those of you headed towards pre-cal, you're going to be doing the algebraic check. Here, we're just going to introduce it to you, and we're going to do it graphically. But what does this equation, let's analyze it a little bit more. So we're saying just f of x is the original function. Oops. And from our transformation lesson, when the negative is on the inside of the function, this is a reflection across the y-axis. Why is it not writing? And the equal to is technically is the same as. So let me just read what I just wrote. The reflection across, hold on. The reflection across the y-axis is the same as the original function. And that's really what we just said here. Graphs are symmetric with respect to the y-axis. Now part C says, if f of x is a polynomial that contains terms that have only even powers of x, and you can have a constant term, then f is an even function. This is pretty neat for those of us that have excellent memory. If you are given an equation and all you see are even powers of x and a constant, without graphing it, you should know. It'd be nice for us to know, oh, it's even, it's even. All right, so now let's talk about odd functions. So graphically, we have two explanations here. If we could spin or rotate the graph about the origin, the original graph would reappear after half a turn. This is having symmetry with respect to the origin. Explanation number two. I won't be able to do explanation one. If I turn my iPad over, it'll just, the page will follow me. But technically, if you were to have a graph, hang tight. For example, like this. If you put it on your sheet of paper, it'd be nice if you did. And if you're gonna do a half turn, you could put a mark here. Let me do it a different color. And if you were to turn your paper half a turn so that this dot appears over here, you would still you still end up with the same green function, which you will, then that's how you would see it's odd. If I turn it, well, I am turning it and I do get the same function, but you wouldn't be able to tell that I am. Okay, so now I'm having too much fun. All right, moving right along. Explanation number two. The reflection across the y-axis is the same as the reflection across the x-axis. Okay, so this one, let's write these in symbolic form. So the reflection across the y-axis, which is f of negative x, is the same as, is equal to, the reflection across the x-axis. So this is negative f of x. Again, this is from our transformation notes. And it part B says algebraically f of negative x is equal to negative f of x. Well, wow, that's exactly what we just wrote down. So here on this one, let me highlight it a different color. I already used that one. F of negative x is this one, and negative f of x is this one. All right, part C, if we have good memory, if f of x is a polynomial function that contains terms that have only odd powers of x and no constant terms, then we have an, if not, we could just graph it and then do what we're going to do right now and analyze it graphically. So examples, it says determine if f is odd, even, or neither. So I'm going to tell you the easiest one to check is even. So I'm going to start off with even. So here with even, in blue is my original function here. And here, I'm going to pick another color. So if I had this point right here in blue, well, I changed my mind. If I were to reflect it across the y-axis, it would end up right here. And the same thing, if I had the original point here in blue, it would end up right here as well. So all of the points are going to be superimposed one on the other. So one other one, just as an example, if I have the original point here and I reflect it across the y-axis, it ends up here. And the original blue point here is going to end up as a red point here. So if I connect the red dots now, technically I'm going to be left with the exact same graph. So this one is even. And again, because the reflection across the y-axis ends up being the same as the original function. Number 2. So let's do the same process here. So if I were to reflect this point right here across the y-axis, I would end up somewhere right here. So right then and there, I know that this is not even. So this is going to be not even because the reflection across the y-axis is not the same as the original function. I did not end up on top, superimposed of the original function. All right, so I'm going to erase this. So here on this one, excuse me. Now for odd. So for odd functions, I'm going to go back and read it again. So again, the half turn, you can take a look at it and see that if you were to put a marking right here and turn your paper so that it appears here on this side, you're going to end up with the same graph, and it's definitely odd. But I'm going to do it with explanation number 2. So here I go. Explanation number 2 says, so where am I? Explanation number 2 says, the reflection across the y-axis. So I'm going to do the reflection across the y-axis very slowly here. So if I have this point here, and I'm going to reflect it across the y-axis, it ends up here. If I were to do this point here, and I were to reflect it across the y-axis, it would end up right here. If I were to do this point here and reflect it across the y-axis, it would end up right here. If I were to reflect this point across the y-axis, it would end up right here. And this point right here, if I were to reflect it across the y-axis, it would stay right there. And so I'm going to do the reflection across the y-axis. And so again, this is the reflection across, excuse me, the y-axis in red. All right, so I'm gonna erase. Now I'm gonna start off with the original blue function again. So I'm gonna go right here. So explanation 2, so I'm right here, says the reflection across the y-axis is the same as the reflection across the x-axis. So now I'm going to reflect the blue function, which is the original function. I'm going to reflect it across the x-axis. So that means that if I have this point here and I reflect it across the x-axis, it's going to end up right here. If I have this point and I reflect it across the x-axis, it's going to end up right here. Excuse me. If I reflect this point across the x-axis, it's going to stay right there. And if I reflect, excuse me, this point right here, it's going to end up right here. And if I reflect this point right here, I'm going to end up right here. So if you notice, and if I connect the dots, my reflection across the x-axis is going to be the same as my reflection across the y-axis. They're the same. Therefore, it's going to be odd. So let me write down what I just put here. F of negative x is equal to negative f of x. Therefore, this is an odd function. All right. Number 3. This one right here. Let's see the reflection here. Let's see if it's even. So if I get this point and I reflect it across the y-axis, it's going to end up right here. So it's not even. So I'm going to put here not even, because the reflection across the, because the reflection across the y-axis, this is the reflection across the y-axis, is not the same as the original function. So now I need to test to see if it's even. And again, I can turn the paper halfway and see that it's not going to be in the same position. And I'll say it's not odd, so it has to be neither. But I'm going to take the time again to do this testing to see if it's odd by graphing each one of the reflections here. Okay, so for odd, I need to do the reflection across the y-axis. So here I go, very slowly. So if I'm going to reflect across the y, this right here turns out to be right here. This point is going to stay right there. This point right here is going to end up over here. Again, I'm reflecting across the y-axis. And then this point here turns out to be over here. And this point here, if I reflect it across the y-axis, turns out to be here. And so if I connect the dots, it's going to look something like this. So it's definitely not even. I did not end up on the same graph. Now I'm going to do the, reflection across the x-axis. So reflection across the x-axis. So here I go. Oh, that's not what I wanted to do. Sorry. So my reflection across the x-axis. So if I start off with this point right here, and I'm going to reflect it across the x-axis, I'm going to end up somewhere here. So if you notice, I can stop right there. I'm not landing on top of the red graph, which is the reflection across the y-axis. So I'm going to stop right there. It's not odd because my reflection across the y-axis, this is my reflection across the y-axis, is not going to be the same as my reflection across the x-axis. So therefore, this one is going to be neither or neither. All right, next one. It says f of x is equal to negative x to the 6th plus 5x squared. So if we have excellent memory and we see that, oh, all of these are just even powers. And I can even have a constant here, but I don't have it. But this is going to be even. This is going to be an even function. So let me write this down. It's even because all powers are even. Oops. Don't be lazy. Now, if you gotta see it to believe it. So here, let's just graph it. So let me zoom in here. Come on, Desmos. So I have negative x to the power of 6 plus 5x squared. And yeah, it's definitely symmetric with respect to the y-axis. The next one says f of x is equal to 1 over x. So just note, this is not a polynomial. Polynomials don't have, can be written in fraction form. So it's not a polynomial. But we can still analyze if it's even or odd. So for this one, if we were to say this is 1 over x here, this is what it looks like. So let me do a quick little sketch. That's not what I wanted to do. I want to get this done. So it looks something like this. So it's definitely not even, because if I reflect it across the y-axis, it's not the same. Hang tight. But if I do my reflection across the y-axis, I would end up with this graph. And if I do my reflection across the x-axis, I would end up with this graph as well. So I can write f of negative x, my reflection across the, again, this is reflection across the y-axis. is the same as my reflection across the x-axis. Another thing you could have done is, if you remember, technically this has a power of 1, and you can rewrite this as x to the power of -1 and say, oh yeah, look, it only has negative. That is not what I wanted to do. It only has negative powers. So yeah, there it is. It should be odd, because -1 is an odd number. Next one, f of x is equal to the absolute value of x. Well, okay, so my graph is giving me issues, but you can graph it, or if you remember how it looks like this. Much better than that. Mine's a little bit off, and the whole point of this is for symmetry. That's a better, let me just stick in this y-axis. Let me solve my own problem. So this right here, the even. It's even because my reflection across the y-axis is the same as the original function. So if I were to put this in green, it's this one right here, and it ends up being superimposed.